It is a trap almost every new engineering student falls into. You get an assignment to design a new automotive component, and your immediate instinct is to fire up your CAD software and start drawing. But without knowing exactly what that part needs to survive, that 3D model is basically a digital fantasy. The moment you expose an arbitrary shape to real-world physics, it breaks. Before you ever open design software, you have to complete step 1, writing the Product Design Specification, or PDS. A PDS is not a drawing. Think of it as a strict rulebook. It lists clear, measurable, and testable targets that define exactly what your component must do, rather than what it looks like. By setting these targets up front, you eliminate arbitrary guesswork. The PDS acts as a reality filter, ensuring your design is mathematically viable before a single prototype is ever manufactured. To build that rulebook, we start with element 1, performance and loading. Cars are highly chaotic, dynamic environments. Your microcomponent is going to get knocked around. To guarantee structural integrity over years of driving, you have to quantify the exact forces it will endure. Will it bear the constant weight of static compression? Is it going to endure torsional twisting from a steering column or relentless cyclic engine vibrations? This graph plots fatigue cycles over time against a required structural threshold. To ensure your part stays below that failure point, your PDS needs exact force tolerances measured in newtons, alongside a required fatigue life. That brings us to element 2, the working environment. A plastic knob sitting comfortably inside the climate-controlled cabin lives a very different life than a sensor mounted right next to the exhaust manifold. Your specification has to lock down the exact minimum and maximum temperatures the component will experience. If you omit these boundaries, your part might warp in the summer heat or crack during a winter freeze. Automotive parts also face a constant barrage of harsh chemicals. Your rulebook must specify the required resistance to corrosive substances like motor oil, gasoline, antifreeze, and winter road salt. By meticulously measuring these invisible physical forces and chemical attacks, you guarantee the component actually survives in the vehicle's harsh ecosystem. Once you have mapped out the loads and the environment, those numbers directly dictate element 3, material requirements. The modern automotive industry relies heavily on lightweighting. Shedding mass from thousands of microcomponents is how engineers squeeze out better fuel efficiency and battery range. This scatter plot charts material density against Young's modulus. To hit that highlighted target zone, your PDS has to set a strict maximum limit for weight while maintaining a minimum requirement for stiffness. These specific data points tell you exactly what to use. High heat and stiffness might point you toward a lightweight aluminum alloy, whereas heavy chemical exposure might demand a semi-crystalline polymer. Selecting your material based on strict numeric targets rather than guesswork prevents structural failure down the road. Next is element 4, manufacturing constraints. How the part is built dictates how it can be designed. Let's look at additive manufacturing, specifically fuse deposition modeling, or FDM. The physical limitations of the 3D printer hardware heavily restrict your digital design choices. To guarantee a solid structure, your printed wall thickness must be exactly 3 times the nozzle diameter. Designing a wall only 2 nozzle widths thick creates microscopic voids between layers. If the component requires an airtight fluid seal, these gaps will completely ruin it. Even if you have the perfect material and the perfect load calculations, your design is useless if its geometry violates the physical limitations of the manufacturing hardware. By defining forces, environment, materials, manufacturing constraints, and target cost, you construct a mathematically sound sandbox for your project. You prove that the true art of engineering happens long before the first line is ever drawn.